graph of f, we're on page 21. What would you say my function is doing here? Concave up or concave down?
Concave down.
Concave down. So then would you agree here, it starts and it turns to concave up. So you guys, maybe what you do is let's go put in a little point. And I'm thinking it's at about negative 0.5. We're going to call that a point of inflection, a POI, because we changed from concave down to concave up. And then do we change to concave down somewhere else again?
Yeah.
We do. Any guesses? It's kind of hard to know. This is why we're going to need calculus to figure out exactly where.
Say 1.5.
About 1.5. Yeah, maybe. I'm thinking maybe a little before that.
Okay.
I don't know. Well, you can just put it about anywhere. The bigger the dot, the bigger the estimation. Yeah, it's somewhere around there, maybe. Okay, yeah. There's another point of inflection because we changed from, and maybe you just write yourself a little note. This is concave down. Then we're concave up. Then we're back to concave down. Okay, so let's go see how we find those points of inflection. 1998, the year that I got bangs. You've heard about this. We don't need to rehash. All right, so points of inflection. We're going to have to go find, again, those critical points. Let's go find those critical points. And so those critical points are when f double prime equals 0 or when f double prime is undefined. Let's go do that. When would f double prime be 0?
When x is 0.
Or?
X is negative 1.
Or?
X is 2.
Beautiful. Is my f double prime ever going to be undefined?
No.
Nah, because we don't have any denominator set equal to 0. So you guys, we're going to just do our little chart. So this is our little Monday reminder of, oh yeah, we were doing these charts on Friday. We've got our little sign chart. Those are x coordinates that we're going to plug into the second derivative to see what my concavity is doing. We got to plug in some tweeners. You good with like a little negative 2? A little negative 0.5? A little 1 and a little 3? You guys, what happens when I plug a negative 2 in to my second derivative? Let's think about this real fast. What will this quantity always be? Yeah, if it's squared, that one's always going to be positive. So I'm even going to say I'm not even worried about it. If I plug in a negative 2 here, I'd get a negative times a negative, right? That's a positive. If my second derivative is positive, yay, we're happy, we're concave up. A negative 0.5 plus 1 would give me a positive times a negative is a negative. If my second derivative is negative, my function is concave down. If I plug in a 1 there and there, I'm going to get a positive. And if my second derivative is positive, we're concave up. And if I plug in a 3, isn't that also positive?
Yep.
Okay, so then look what they're asking. Where do we have points of inflection? And this is a point of inflection is where we change concavity. If we change concavity, where's that happening at? What x values? Negative 1 and 0. Did we change concavity at 2? It went from up to up. We did not. So they're trying to throw you off. Negative 1 and 0, is that C? Mm-hmm. Yeah. They're trying to throw us off, people. They want you to say, oh, my critical points, negative 1, 0, and 2. Boom, E. But we had to double check it. Now this one, also 1998, what is the coordinate of the point of inflection? Which again, they just didn't give us the second derivative like they did up here. So we got to go find that second derivative. What would the first derivative be? Let's go name that a little y prime. X squared plus 10x, good. The second derivative?
2x plus 10.
You got it, dude. So there's my second derivative. You always are curious what that critical point is. So go set that equal to 0. Oops. X is negative 5. Funny. I actually amended this question. I think I added the E because my kids were just jumping to it. And I was like, ooh, this early in the game, I feel like we need to actually see, does it change concavity at negative 5? So negative 5 is going on my number line. We're going to plug it into my second derivative to see what my function's doing. You down plugging in a little negative 6, a little negative 4? As my betweeners. If I plug in a negative 6 to that x, would I get a positive or a negative second derivative? Negative 12 plus 10 will get me a negative. That means my function is concave down. If I plug in a negative 4, I'd get negative 8 plus 10 is positive. My function's concave up. Do I have a point of inflection at negative 5? The answer is yes, because my second derivative changed signs. Boom. As we look at this, you guys, it says how many points of inflection does a graph of f have? If I were you, I would just remind myself like, oh, that's when my second derivative changes signs. When my second derivative changes signs, that's when we have a point of inflection. Let's go look at a graph of my second derivative. Oh, and they give us a window too. You guys see that? 0 to 3. So I'm going to go to my y equals screen. I'm going to go type in that function, sine of 3x minus the cosine of x squared. And I'm going to change my window from my x min to 0 and my x max to 3. I'd also make your y min negative 1 and your y max positive 1. When I go sketch this, if I were you, I'd sketch that graph. I'd say it looks a little something like this. Again, accuracy is not important, but I would let myself know, oh, this is a graph of the second derivative. When does that second derivative change signs? Negative to positive, positive to negative. It happens 5 times. We down with that, people? So when does that second derivative change signs? We are looking at when that f double prime has some zeros. Not only just zeros, we got to make sure it actually crosses that x-axis to change signs. Cool, cool? Harvey, you good? All right. Okay, 2015, no calc now. It says, where does it have a point of inflection? And like, okay, a point of inflection is when f double prime changes signs. I should add that to my little chart here. Point of inflection, f double prime changes signs. Okay, so it says we need f double prime. What'd they give us? F prime. Let's go get f double prime. F double prime would be, appreciate you, if something changes signs to go from positive to negative or negative to positive, it's across through 0. So let's go set it equal to 0. Add my 4, divide by my 3. And then what's the square root of 4/3?
2 square root of 3.
Yeah, because isn't that really the same as square root of 4 over the square root of 3, which is just 2 over root 3. And then some of you might be trained from your pre-calc and algebra 2 days, oh, get rid of my square root out of the denominator. But look at their answer. If it is this answer, I think we can just leave it. Okay. We got to make sure, is it actually happening at 2 over root 3? Do we feel good based on these answer options that has to be it? It's my only critical point. So if we're on a time crunch, you could totally, Bob is definitely just going to say, I'm going here, I'm not making a sign chart, but I'm going to prove it to you. But Bob, on this one, that would be fine unless there was an answer that said, like, there is no point of inflection. So I'm going to go plug that into my second derivative to see what my function's doing. I'm going to say something smaller than 2 over root 3. I'm just going to say 0. And something bigger, I'm going to say 100. Who cares? I don't know what 2 over root 3 is, so I'm going to make something big. We got to go plug it into our second derivative. If I plug a 0 in over here, you agree my second derivative would be negative? And if my second derivative is negative, my function's concave down. And if I plug in 100 here, 100 squared times 3, and then if I just take away 4, it's positive. And if my second derivative is positive, it's concave up. Do we have a point of inflection at 2 over root 3? Yes, because my second derivative went from negative to positive. It changed signs. Boom. Let's see it. Okay, he says, hey, here's f. Whew, what is the x-coordinate of the point of inflection when the graph changes from concave down to concave up? That's how specific they want us to be. Okay, we know points of inflection where my second derivative changes signs. Let's go find my first derivative. Derivative of the first plus, love it. We got to go find that second derivative. Negative sign minus cosine. Is that right, y'all? Good, good. Okay. We always just have to set that equal to 0. Let's go see where that equals 0. Yeah, this is a little unit circle review. You want to add cosine or add sine to the other side? I don't care. You want to add cosine? So we got, when does negative sine equal cosine? Think about that unit circle. When does negative y coordinate equal the x coordinate? Or you can think, when are they equal, except the y is negative?
They'd be equal at whatever the 4 is.
The 4s, you're saying. The root 2 over 2, root 2 over 2, I agree. When is the x equal to the negative y? Say that again. 3 pi over 4. So if we're at 3 pi over 4, we're going to say at x equals 3 pi over 4, because that coordinate, if anyone can't remember, is negative root 2 over 2, root 2 over 2. And that's at 3 pi over 4. When will that happen again?
That would happen at...
Yes. So if we get 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4. So that's 7 pi over 4. We had root 2 over 2, negative root 2 over 2. So we're going to say those are my 2 critical points. Look at these answers that we're seeing up here. 3 pi over 4, 7 pi over 4. One of them is right. So we got to go plug those into my sign chart. 3 pi over 4, 7 pi over 4. Just making sure I gave you guys enough room because this is a lengthy one. Plugging those into my second derivative. Okay. Notice that we do have some bounds here. So what do we want to plug in? Could I plug in a 0? I could, because it says greater than or equal to 0, so we could plug in a 0. What do we want to plug in between 3 pi over 4 and 7 pi over 4?
Let's put in pi.
I'm down with a pi. Bigger than 7 pi over 4? 2 pi. I agree with that, because look, we're bounded over here. Okay, if I plug in a 0 into my second derivative, the sign at 0 is 0 minus cosine at 0 is 1. So we'd get a negative. If I plug in a pi, the sign at pi is still 0 minus the cosine of pi.
0.
Cosine of pi. Isn't that negative 1? So wouldn't that be 0 minus negative 1? Wouldn't that be plus? Okay with that, Koopy? Pi is over here, buddy. So we'd have negative 1, 0. So add a pi.
Okay.
We'd have a negative 0 minus negative 1. And then at 2 pi, that's back over here, we'd have 0 minus 1 again.
Yeah.
And look at what they asked, though. What is the x-coordinate of the point of inflection where the graph changes from concave down to concave up? Where did that happen? At 3 pi over 4, down to up. Yep, 3 pi over 4. Let's go get through this page, and then we'll call it, people. The function f is defined from here to here with a calculator. That's good to know. We got a window. First derivative is this. Which of the following statements are true? Okay, I'd say let's go look at our calculator real fast. If we're talking about mins and maxes, let's go take a peek at that f prime graph. So let's go to our y equals screen. I'm going to graph my function that they gave us of sine of x squared. And I'm going to change my window to have an x. I'm going to go actually zoom standard real fast. Then I'm going to change my window from an x min of 0.4 to an x max of 2.4. I'm going to just note, I'm going to just kind of sketch that this is f prime. F prime looks like this, f prime. And they said f has a max somewhere between 0.4 and 2.4. For our function to have a max, I put it right next to Riley's head. For us to have a max, my f prime, for my function to have a max, my f prime has to go from positive to negative. Do these f prime values go from positive to negative somewhere on this little graph? Yeah, that would be happening right here. So right for 1, I'd be like, yep, it is. Do we have a minimum? For my function to have a minimum, my f prime would have to go from negative to positive. Does that happen on my interval?
Yeah.
Does it? I don't think so. Not that because it's not on the interval, right? You're like, maybe outside of 2.4, but not on the interval they gave us. So nope, no minimum. Okay. And then points of inflection. You're like, what? You guys, a point of inflection is where the second derivative changes signs. Second derivative. Two different ways we can do this. We're staring at a first derivative graph. So I could do it from this graph. When would this, what's going on here? What is my f double prime here?
0.
Careful, my f double prime, because that's the slope then of f prime.
Yeah, it's 1
It'd be positive, then
negative. Positive.
Positive. So did my f double prime, we said my f double prime has to change signs. How many times did that happen? Positive to negative, negative to positive, how many times? And they said the graph has 2 points of inflection. Are you down with that?
Yeah.
I agree. So 1 and 3, it's going to be D. But I do also want to show it to you from an f double prime graph. So check this out. I'm going to say, hey, what's the derivative, math 8, of that function, sine of x squared?
It is 2x cosine of x squared.
Did you remember chain rule?
Yeah.
Oh, yeah, you did. But I'll let my graphing calculator do it for me, right? If this is a graph of f double prime, I'm even going to just sketch it so we got it. Does my f double prime change signs twice?
Yeah.
Yeah, positive to negative, negative to positive. So you could have done that from either graph. Sound good? Okay. Woo-wee, this one's a lot. This one's also calculator active. It says f, g, and h have second derivatives given above. Which of the functions have a graph with exactly 2 points of inflection? And that's where my second derivative changes signs. And bless up, we've got a calculator. But look, are they pretty similar equations? They're pretty similar, I agree. I'm going to go graph that first one, and I'm going to say x times x minus 1 squared times x plus 2 cubed. And I'm going to do a zoom 6, just my basic window again. And I'm going to say my f double prime graph. F double prime is looking something like... This is my f double prime graph. How many times does it change signs, would you say? Say it again. Yeah. Looks like, correct me if I'm wrong, it's happening once here, positive to negative, once here, negative to positive. You guys down with that? So F, it says which one has exactly 2? I'm digging F. And then I'm going to go to my y equals screen, and I'm going to just literally, let me teach you guys a trick. Do you guys know this on your y equals screen? Just hit second right arrow, and it takes your cursor all the way to the right.
Huh.
Ooh, second left arrow takes your cursor all the way to the left. Anyone know that?
Never knew.
Now you do. What happens when I shift that up 1?
Yeah.
Do we still have 2 sign changes?
Yeah.
Yeah, and if you maybe you want to let yourself know. Oh, it was going here. This was now G double prime.
But H won't because since it's down 1. On F, and with normal F, it'd be right at the board.
I am picking up what you are throwing down. Picking it up.
See? There's
So-
4 now.
Is there 4? 1, 2, 3, 4. You right. So on H double prime, that graph is looking like a lot is going on. Ooh. Woo. We got 4. 1, 3, and 4. No H. So our final answer, C. Concave up. Concave up just means that second derivative is positive. These are things we got to start remembering. Second derivative with a calculator. Which would we rather look at? Would you rather look at a graph of f prime and do it, which we could, or a graph of f double prime? It doesn't matter. Double prime, let's do it. Because our calculator can find that second derivative for us. I know you could, but let your calculator do it for you. Let's go to that y equals screen. Let's do math 8. X to the 4th. Minus 6x squared. Minus 8x. Minus 3. You guys, when you wanted to graph the derivative, You do x equals x, just so you know. So when I let it do the graph for me, the second derivative for me, my graph looks like this. That's the second derivative. It says, what intervals is my function concave up? That's when my second derivative is positive. So is my second derivative positive here? No, all those y values are beneath the x-axis, beneath the x-axis, beneath the x-axis. My second derivative is going to be positive from that 0. Whoops, that is huge. From this 0 and everything above the x-axis. So I'm going to do second trace option 2 for 0. I'm going to go to the left and to the right. And did y'all get that too? That was a nice point. So where is that function concave up? 2 to infinity.